When forces in the Earth's crust cause faults to slip, the result is a rapid release of energy in the form of an earthquake. Although the changes that occur during an earthquake are fast and readily apparent, other, slower motions of the crust manifest over days or even months as plates slip and creep. Some of these slower geological motions, or strain transients, are so gradual that they have only recently become measurable with the advent of GPS and satellite measurements over time. A common explanation for these phenomena is that the friction controls the dynamics of faults and shear zones. Yet, strain transient motions require an explanation that also considers how rock behaves when it softens under heat and pressure, and friction becomes less important. Under the high temperatures and pressures found deep in the Earth's crust, rock exhibits a combination of brittleness and ductility, akin to a candy bar made of brittle nuts and ductile caramel. To understand how strain transients arise in rock under these brittle, ductile conditions, researchers analyzed the response of Carbopol, a polymer material, to increasingly forceful shearing. Carbopol is both brittle and ductile. During deformation, parts of the carbopol break, while other parts flow. The polymer can manifest different material strengths through its tunable yield stress, which is the maximum stress from which a material can snap back. With higher yield stress, the polymer imitates cooler, more brittle rock, while lower yield stress mimics the hotter and more viscous rock found deeper in the Earth's crust. During the tests, a spring-loaded frame applied shear deformation to each sample. The low-yield stress polymer formed a fracture where the two halves slid past each other, but the stick and slip, common to rigid materials, was smoothed by ductile stretching and bending into a slower, creeping motion. The high-yield stress polymer, in contrast, developed tearing fractures throughout. As the deformation increased, these fractures proliferated in bursts, with the material slipping each time. Eventually, the increasing force overwhelmed the strength of the unfractured material, producing a fracture and leading to a stick-slip motion. These observations suggest how rock can react to stress under the varying temperature and pressure conditions of the brittle ductile behavior, generating strain transient phenomena governed by the properties and dynamic changes of the rock rather than simply by friction between rigid masses. Explaining these slow transformations provides another important element to our understanding of the phenomena that shape the Earth's surface.